Our pressure, if you're just picking up the screencast right now, you missed the in-class demo, but just imagine it was really good.
Professor, we're still looking at catalyst.
Oh, thank you. Are you saying that's not good enough?
I mean, I liked it.
I mean, it's nice, right? It's good stuff. So our pressure drop terms that we've experienced so far have looked something like this, right? That was an approximation that we saw. The general form that we use was the Ergun equation, which I do not have off the top of my head. dP dz is equal to a big function of all kinds of things that have to do with the reactor geometry, or more likely the reactor specifications. So when we wrote out that big function, I didn't define all of those terms by themselves. You will have to figure out what all those terms mean in order to do either one of the projects. They both use that same reactor, that same expression. But the key point is they're all constants. They all have something to do with how big are these little pellets that I've got in here, what's the geometry of the reactor that I'm dealing with, what kind of fluid am I trying to pump through there. So as a first approximation, we don't really need the full differential form of the Ergun equation. These two, or sorry, this one is just fine. We can get away with a qualitative description of a pressure drop that looks like that. The Ergun equation is going to change that shape a little bit. It won't go quite to the 1/2 power, but that's still a pretty accurate approximation of what the Ergun equation does. That's okay. There's no problem with that side. The problem comes in when we try to calculate our pressure inside the reactor. And you can try this on some of your homework problems. If we plot W and pressure, initially we start off with some pressure P naught. According to that equation up there with the red check mark, this one, the pressure is going to fall as we go down the length of the reactor. It will fall until it eventually gets to 0. Actually, we know exactly when it hits 0, because if this term is ever equal to 0, then the pressure in the system is also equal to 0. So there's a special point. If you ever have 1 minus alpha W is equal to 0, this is no flow. Why is it no flow? We'll get to why it's no flow in a moment. That happens to occur at a special condition of whenever 1 over alpha is equal to W. That's actually, instead of no flow, we'll describe flow in a minute. There's no pressure because pressure is 0. So let's put that special point on our plot over here as 1 over alpha. What's happening to our pressure in between the amount of catalyst that we experience prior to 1 minus alpha and the amount of catalyst we experience after 1 minus alpha? Generally, the pressure is going down. I'm going to try to draw this as a somewhat curved line. Nope, that's a bad one. Don't try to sketch this until I get it right. There we go, that's better. It's going down to 0 pressure. The pressure in the reactor when you get to an amount of catalyst equal to 1 over alpha is exactly 0. You've run out of pressure. Do we have to stop our ODE solver at that time? Can I set the value of W to something greater than 1 over alpha? Sure, ODE 45 doesn't care what we set 1 over alpha to. We can set it to be anything we want. We can put 1,000 in there. The equations that we've got don't break. There's nothing wrong with putting in a very large value of alpha inside that expression for P, or for that matter, there's nothing wrong with making a really large reactor that obeys the Ergun equation. There's no problem with that. The problem comes in when we actually calculate what that pressure is. Eventually, that pressure will go negative. So down here we have P is less than 0, and up top we have P is greater than 0. This is what we saw when we had our two gentlemen up here demonstrating something, which was if we make the reactor big enough and we only apply a certain amount of pressure P naught here, we may not be able to get flow to go all the way through the system. When you experience P is less than 0, well, you actually can't get P less than 0 in most cases. You really just stop the flow at P is equal to 0. So if you imagine a reactor underneath here, you've probably got room to add the reactor, but I don't. If you imagine your reactor is this big, and you have this special point of 1 over alpha, and you assume that there was flow going into the middle, into the entrance here. So that would be what the equivalent of the two. This is supposed to represent our volunteer a few minutes ago, putting some pressure onto the system. The pressure that he was able to apply with his lungs is, I would guess, maybe 10 psi, maybe a little bit less. So initially what this equation is saying is you do have a little bit of pressure. As long as you have a little bit of pressure, or more specifically a little bit of a pressure gradient, you can get flow to go. So that arrow continues here. Every time I move along that pressure gradient, actually the gradient itself stays roughly constant, but it does go down a little bit. So the flow reduces a little bit more each time. So we can imagine these arrows staying roughly constant, but then they start getting smaller because the flow is being reduced. Until eventually you get right up next to that red line where you can't have any flow anymore because you no longer have a pressure gradient. If you were to extend, or actually you no longer have, pressure gradient. You no longer have a pressure gradient because the pressure itself can't really drop below 0. The equation has no problem, right? It will say, sure, you've got pressure and the pressure is negative. But in a real system, you can't go negative on something like pressure. It's an absolute value, kind of like temperature. We can't get to a negative temperature. Actually, there is a way to do that with quantum mechanics, but it's kind of shifty. They just kind of cheated a little bit. From the definition of temperature that you learned in thermo, there is a way to cheat and get negative temperatures. Anyway, we can't have negative pressures under any of our reactor conditions, so the flow just stops. This represents what I said before, which is an accumulation inside of our reactor. The equations for fluid mechanics that you either are currently learning or will learn in 101A have no problem with a situation like this. They will not let you go to negative pressure. But because we're sort of using them on an ad hoc basis with our reactor equations, it's possible that the two assumptions will not agree with each other. So the assumption that we make on our reactor equations is that there is flow. So whenever we write an equation like V is equal to V naught times all of these terms, Ft over Ft naught, the pressure terms and the temperature terms, that makes the assumption that we started off with some flow. We started off at steady state. That doesn't mean that our pressure equations will allow us to get to that steady state or allow us to maintain that flow. Every once in a while, if we put a poor set of assumptions together, those two will conflict and our pressure will turn negative, but there's nothing wrong with these equations that'll make anything break in terms of the equation goes to infinity or something like that. It'll just switch signs in there. Usually the effect of that is if you're running your simulation and, for example, you look at I don't know, X, something like that, any of these terms, you'll see them going along, normally, something like that, and then they shoot up. You'll see a cusp point in there somewhere. That cusp point, where everything seems to change, is typically what happens when you have a negative pressure inside your system. Again, there's nothing wrong with the equations that we have for reaction engineering that say, something weird happens when we go negative pressure. It's just we're not using the full set of fluid mechanics equations that say you can never actually have negative pressure. Yes?
So how are you getting negative pressure out of this? Because it's taken to the square root. Shouldn't you be the imaginary number if that term becomes negative?
Well, no, that's what I'm saying is you can't actually go negative.
But the plot is from that.
I'm saying, imagine that's what this is predicting, right? It's saying initially it's falling. So conceptually what these equations are saying, the one on the top is an oversimplified version of the Ergun equation. Conceptually what they're saying is the pressure is falling. If you continue them past 1 over alpha, presumably if you put them in the full Ergun equation, it'll just keep falling. The simplified equation may or may not. say something like that. Although you can still have a negative version. You'll just have an imaginary component to it. Which is I mean, MATLAB unfortunately can handle imaginary components, which does not always make our lives easy. So where is that energy going? Why aren't we able to account for that energy? The reason we can't account for that energy is because it involves an energy balance term that we haven't introduced in this class. The energy balance that we have assumes that there are no viscous losses inside the system. So when somebody's trying to blow air through one of these tubes, you're imparting energy into the system from your lungs, right? You're squeezing on it, you're moving some of that air out. When you get to fluid mechanics, you'll see that we interpret that as energy. That energy is being lost. It's no longer going to driving the flow because those air molecules are bouncing along the surface of things. They're actually heating up a little bit. All that energy is getting dissipated as heat. In addition to the fact that we have hot air going through there, we're actually heating those up a little bit, each of the pellets, because we have to get rid of that energy that we put in through our lungs. None of that is captured in our equations of our terms of energy balance in this class. If you wanted to capture that, you would have to couple those two equations. We don't have any problem doing that. We do it in 101A all the time, but we just don't include that as part of our energy balance, so it's not something that we're going to see. When we have our energy balance, we drew a control volume around an element of our reactor, right? We drew a little control volume, we put spheres in there, and we said, what's happening to the energy inside there? The only energy that we worried about was a little bit of energy coming in from our flow, a little bit of energy coming out that's being carried out by our flow, any energy that's given off or absorbed by the reaction, and any energy that we can pump in through the walls, through something like a heat exchanger. The type of energy that we were missing in there is this dissipation energy. Where does that pressure drop go to drive flow, and how does it get eliminated? It usually goes through temperature. The effects on temperature are pretty small, especially when you're worried about a chemical reaction where the temperatures can change by hundreds of degrees. But that effect on flow and through things like the pressure drop can be quite significant. If you account for both of those, then you never have to worry about these pressure drop problems. The downside is you now have potential of getting into a situation where you are no longer at steady state. You could be in a situation where you have accumulation, and then again, you're not going to be able to use any of our equations because they were all derived assuming you were at steady state. So if you use the full set of equations, most of these problems go away. You won't have a problem with it. But it is still possible to just poorly design a reactor. If you make it really, really long and you only apply a certain pressure at the beginning, you will not be able to force flow through the whole thing. To figure out whether or not you've got a big enough reactor or too big of a reactor, we do have the tools to figure out how big that can be through the Ergun equation. But if you want to know why we came up with the Ergun equation and what it represents, where are these terms going that result in a pressure drop, you'll pick that up when you get into 101A. The equation that you're looking for, because I know you'll all remember this when you get to 101A, is the energy Bernoulli equation. Pay attention during the derivation of that equation, and you will see which terms originate or which terms lead to this effect of losing energy due to flow. We usually use the energy Bernoulli equation to represent exactly that kind of a loss, which is just pumping something through a pipe reduces the energy available to drive that flow. You lose some of it to the walls because those molecules get stuck on the walls. They slow down. We have lots of other terms. Who's in 101A right now? Anybody?
No one's in 101A right now.
Who took 101A? Perfect. What are some of the ways that you can lose energy?
The length of a pipe.
Length of a pipe. What?
Coupler.
Couples.
Valves.
Valves.
Gravity.
Sharp turns. Gravity. I can restrict the pipe. I can have stuff on the walls of my pipe. Anything that sits inside that pipe, even the presence of the pipe itself, represents an energy loss term that we have not encountered in this particular class. I'm glad some of you took 101A because you actually know what I'm talking about when I say energy Bernoulli, and I'm sure you could all write it down off the top of your heads too. Anyway, this is what happens with pressure if you happen to run the equations a little bit too far. There's nothing wrong with the equations you've got. You just have to be aware of the limitations, which is that you haven't accounted for a momentum balance on the fluid or other terms inside the energy balance. Any questions on pressure? Yeah.
If you do use the energy Bernoulli, is it clear when it would not become steady state, or would you kind of have to figure it out?
No, actually, the energy Bernoulli was derived assuming it had steady state.
Oh, okay.
Yeah. So you're really in trouble if you get to a point where you stop the flow, because almost every equation we deal with, whether it's in reaction kinetics or in fluid mechanics, assume that you start at steady state.
So I guess what I'm asking is, if you're using that equation and it happens to not be at steady state, would you be able to know utilizing those equations, or would you have to discover it some other way?
Usually you'll discover it by something like this.
Okay.
Something weird happens, you expected it to be smoothly varying from one side to the other, and it's not. Any other questions on pressure? Actually, an interesting side note, math. I'm just going to start a new page. If you look at any of our reaction rates, if you have something like dC, d, let's say T, usually that is going to be equal to some function of C. For example, Kc, probably minus Kc. There's a reason that we use a form like that. What's the rate of change of C when you have no more C?
0.
0. That is sort of a natural regulating method of concentration that forces concentration to always be positive. If you start off with a positive C, even if you start decreasing the amount of C, as you get closer and closer to no C, so C is a function of time, you get that exponential decay where you get really, really close to 0, but you never actually go 0. That's baked into this equation. You'll have a different set of situations if you ever say something like dC dt is 0th order, something like minus k. Now you can go negative, right? If you run the thing long enough, you'll eventually get this negative because the result of that is a linear expression instead of an exponential. This is the same problem, this latter one. This is the problem, or quote-unquote problem, that the Ergun equation has. If you look at something like pressure with respect to, I'm just going to say time, it's really more volume. Let's use volume, or W. The important thing is that it is not a function of pressure. The pressure term doesn't show up on the right of the Ergun equation, which means it doesn't have that sort of self-regulating behavior that our material balances do. It's only describing the amount of pressure drop you have going from one unit to the next, but you can still run into problems of, for example, having negative pressure, like we saw before. So anyway, that's the mathematical reason of why is it I can run a reactor as long as I want, and I never get negative concentrations, but I can get negative pressures. It's because of the terms that show up on the right-hand side. You don't get that exponential decay anymore. So you can go straight through 0 if you try. Math side note. How do you catch it if you have negative pressure, or something that looks like negative, or imaginary pressure, or something like that? Yep, the plot changes shape most of the time. There are a couple of other ways you can throw a piece into your code that looks for imaginary numbers. You can throw a piece into your code that looks for negative pressures, and just stop the code if you ever experience that. The way I usually check it is I just plot the pressure. And if I see some kind of a change in the shape that I'm not expecting, if it's an abrupt change, certainly, that's usually a flag to me that something is wrong with the pressure. All right, the other topic, which I think this is about all we're going to have time to get to today, had to do with this sum of Rij delta Hij term. The example that we were going over, which what we're going to talk about is not unique to this example, it would occur on any of our examples, was that A plus B goes to 2C, and 2B plus C, oh, where'd you go? Come on, there you go, goes to D. And we had some enthalpies here. One was delta H, with a circle was equal to something, and a delta H with 2B with another circle was equal to something else. And we were trying to come up with, how do I write an expression for Rij delta Hij? If you're comfortable with writing that Rij delta Hij term, then the next few minutes won't be anything other than something that you're already comfortable with. But it can be a little bit confusing the way that we're interpreting that sum, because we have another term in the energy balance that looks like the sum of flow rates times heat capacities. That sum of flow rates times heat capacities was the easier of the two sums to work on. We said this one just runs from I is equal to 1 up to, I think we use n as the number of species. So if the species is present, there is a term that sits inside here. So this Fi CPI would look like Fa CPA plus FB CPB up to all of our components, including potentially if you have any inerts. Right, so there's not a lot of mystery behind what that sum means, and there's not a lot of different ways to write it. There's only one free variable in there, which is I. If the species exists, it has an I component to it, and therefore there is some flow and there is some heat capacity, and it must be included in that term, regardless of whether or not it's participating in the reaction. But the terminology that we use for Rij delta Hij has resulted in the following question. Why should I not write, I'm going to do this in red, just so you know that this is not how we write it. How come we can't write Rij delta Hij? And I'm going to use this example up here to write this as the following. I want to write R1A delta H1A plus R1B delta H1B plus R1C delta H1C. So that's for reaction 1, right? I have one term for each of the species that occur in reaction 1. I also need one term for each of the species that occurs in reaction 2. So this is R2B, wait, where was mine? Yeah, 2B, delta H 2B plus R2C delta H 2C plus R2D H2D. Why is it I can't write something like that? The short answer is you're overcounting energy, but we're going to try to, I'm going to give you an example which, keep in mind that whenever we use analogies when we're talking about energy, it's very dangerous to talk about analogies for energy, because energy is not a thing. You cannot pick up energy. You cannot go into a lab and design an instrument that says there is so much energy inside this object. Energy is one of these weird things that we learned about the world, where if I have a system and I look at it, I close my eyes and it goes through some sort of a process, and I open my eyes again, there are certain numbers that I can calculate about that system that do not change. One of those is something that we call energy. But it is not a thing. I am about to use an analogy that assumes that energy is a thing. It's a little particle or something like that. That is not the case. There is no, I can't lift this up and take it into a lab and pull out the energy from it and collect it in a box or something like that. But nevertheless, that analogy is the one that I'm about to use because it can be helpful if you're trying to account for where these numbers are coming from and where they're going. So I'm going to focus on one of these reactions. I'm going to focus on the one on the top, just this one. And we're going to look at a molecular point of view for what's happening inside of here. So we're going to have the reaction A plus B goes to 2C. So our molecules of A are going to be squares. Our molecules of B's are going to be circles, and our molecules of C are going to be triangles. right? So we end up with 1 square plus 1 circle goes to 2 triangles. Inside each one of these, represented at least in mathematical terms by the internal energy U, is something that we call energy. In order to represent that energy, I'm going to use stars. Can you see the yellow stars? Yeah, you can see the yellow stars. So molecule A might have some internal energy that's stored within its bonds or within the shape of the molecule or between charges or something like that. Of 2 stars, B has 4 stars, and C only has 1 star. Energy balances say that if I can somehow figure out what those stars are, remember they don't actually exist, but we can calculate a number that sort of represents a star, and we call it energy, that is something that has to be conserved. If we start off with 6 stars on the left, and it appears that we only have 2 stars on the right, those other 4 stars are there somewhere. It's just we usually don't include them as part of the reaction. But those stars in the shape, or actually energy in the form of those stars, have to be retained. You can't destroy them, they have to go somewhere. Where they go depends on what the system is that you're looking at. If you have a jacketed reactor, maybe those stars get sucked out through the walls and they heat up some of the coolant fluid. If you have a bunch of inert or you have other species in there and you can't take any of the energy out, that energy gets absorbed into other species and tends to raise their temperature. That's why we observe the effects that we do with something like an adiabatic reactor. This is somewhat similar to, remember we saw that H is directly proportional to U. In fact, in some cases we said it was exactly equal to that. Our enthalpy here would be something like 2 for the A, 4 for the B, 1 for each of the C's. As a result, we would calculate something along the line, I'm going to switch back to black because that looks weird. Our delta H looks something like 1 plus 1 minus 2 minus 4, which is minus 4 stars. The units on that, you can see if I switch the star to a joule, now the analogy works pretty well. But the units on that were a little bit funny. We were free to pick those units however we wanted, within reason, right? We had to pick them on a basis of one of the molecules that was occurring in here. So for example, we could have said that you get 4 stars for every mole of A reacted, or you could get 4 stars for every mole of B reacted, or you could get 4 stars for every mole of C produced, except that we're producing 2 moles of C. Right? Every time we react an A and a B, we actually get 2 particles of C. We don't just get 1. So the denominator changes a little bit depending on which one you're talking about. Just to make this analogy work, actually this one has to be positive because you're creating that much. Just to make the analogy a little bit easier, we're not going to worry about sign changes. We're just going to try to calculate the magnitude that gets released. So instead of equals to, we're going to say approximately equals to. So if I want to know the energy released, by this reaction, anytime I have A plus B goes to 2C, I can calculate it in a number of different ways. For example, let's say we have a reactor. Here's our reactor. And initially inside the reactor are 2 particles of A and 2 particles of B. If we let that reactor proceed, maybe somehow we get to complete conversion, we now have 4 particles of C. And then the question becomes, when I write those delta H terms, whenever I write the enthalpy of reaction of a term, I'm dealing with a system that looks something like this one that I've got here on the top. I have taken an idealized system where I react exactly in this case, exactly 1 mole of A with exactly 1 mole of B, and I produce exactly 2 moles of C. How do we take that idealized system and translate it to reality? well, we use the trick of the sum of Rij delta Hij, but we can see if we just want to add up what's happening inside of here, we know conceptually how many stars do I have to have? How much energy has to be released here? Eight stars, right? It's twice as much as what we started off with in our idealized case. So however we calculate our sum of Rij delta Hij, we have to come up with 8 stars. 1, 2, 3, 4, 5, 6, 7, 8. This is what the sum of Rij delta Hij is trying to say. If we shift from the idealized case of just the enthalpy of reaction, which is usually at 298, how do we use that and figure out what's actually happening inside our system? How do we calculate how many stars have been released? We know if we just count the stars, well, I've reacted basically that base reaction twice. So how do I add up those stars if I just wanted to use math? We can't actually sit here and count on the order of moles of stuff, nor can we actually isolate energy, so we have to come up with tricky ways of doing things, which is that sum of Rij term. If I wanted to figure this out, I can start off with that delta H term, right? I could say I should get, oh, I forgot my stars over here. I forgot my units. Right, those are 4 or so. The Rij term is trying to say the following. I always get 4 stars per mole A reacted. If I want to know how many stars I got, I have to multiply by the number of moles of A reacted. If I look at my previous example, that was 2. Right, so the end result of that equation is that I would expect to release 8 stars. But there are 2 other ways that I can calculate that quantity, right? I don't have to use the basis of A, I could use B or C. But I know conceptually, just because this is a simplified example and I can actually count stars, I know I have to come up with 8 stars. That's how many stars were released from a basic energy balance that we saw up on the top. So I could also write 4 stars get released per mole of B reacted. And I reacted 2 moles of B, and therefore I again got 8 stars. Or I could do it the third way and say I get 4 stars per every 2 moles of C formed, and I formed 4 moles of C. Guess what? Again, I get 8 stars. Each one of these, you can pick any one of them. This one represents R1A delta H1A. This one represents R1B delta H1B. And this one represents R1C delta H1C. So as long as I account for which molecules I'm talking about, it doesn't matter the basis that I choose for that reaction. So maybe now it becomes a little bit more clear as to why I never write it like this. If I do something like this, I'm overcounting the amount of energy that got released by the number of terms that I've got here. So there are 3 species that react, so I would be tripling the amount of energy released if I write something like this. That's the equivalent of adding up these stars. Right? If you were to add up all of those terms, you would end up with 24 stars. Which is obviously not the case, right? We can actually track the stars in the simplified case. We know we don't have 24 stars. So if you write that sum out and you include 1 term for each reaction for each species, now you're in trouble because you're overcounting the amount of energy that got released. The way that we set those equations up, the delta H and the Rij, is the signs are going to change in exactly the right parameter to overcount every single time if you use them all every time. So that's why the sum of the Rij terms, this one, when we write sum of Rij delta Hij, it's really only a single term. It's only a single sum. But the sum has changed. Now the J goes from 1 to, I think, Q, was the parameter. This index I here, it's not a term over which we are summing. It's not the same kind of I that we saw with sum of Fi CPI, right? This is saying you need to pick an I. For every time I write out a J, for a reaction J, pick a single component for that species, or sorry, for that reaction, and write everything in terms of that particular species. If you do what we did here, where you add up all of those for all of the species that react in a particular equation or reaction, then you get too much energy because you have overcounted everything. This is why the end result of a term like this for the example that we have looks like R1A delta H1A plus R2, pick another one, B, delta H of 2 in terms of B. You can change these terms, right? If I don't want to work in terms of B, that's fine. I can switch them both to C, because C also appears, or I could switch them both to D. D would also be okay. But I don't add those terms on top of it because then you're going to overcount the amount of energy that shows up. And so the I term that shows up in here is subtly different than the I term that shows up in here where it's FICPI. Right, so they're slightly different. Or actually they're considerably different. But they're all there because of the way that we wrote those reactions to account for adding up energy inside a system without overcounting. But you have to use the sums, right? So if you already had no problems with the Rij delta Hij term, you can forget all the stars. If you were struggling with that a little bit, I hope the stars help a little bit. Please don't walk out of here and ever tell anybody that energy is like stars and you can count it up. Because you cannot grab a star and count it or anything like that. But the analogy can be helpful in some cases. I will see everybody Friday, and our exam is Monday. Thank you all very much.